What's it?
Okay, we're live. Okay, so I said yesterday we were gonna just discuss, you will be, actually, let's just do, we'll do 8. So Albert, Bob, and Charles. Introducing a new character. I know it's very cutting edge.
We're moving up in the world.
Wow.
We're in advanced physics now. 3 characters, not just 2.
I'm just going to move up to the 4th one. Like, what's the name?
It's gonna be Daryl.
I was kind of hoping for something else.
I know you.
Uh-huh.
Have you ever taken an advanced, like, graduate level creative writing class in university? You just they're like, oh, what do you come up with here? And you say, well, here's my story. Consider Albert, Bob, and Charles, whose masses are 50, 60, and 70 kilograms respectively. The professor like shed tears. Beauty, how? Oh my God, I'm so moved.
Every time.
Like if you cry every time. Okay. So here's Albert. Albert, Bob, Charles. So the question is, we're just comparing. Basically, this question is just exists to be a demonstration of like how do you calculate the amount of work done by someone if you know their mass and you know their change in speed. Now, a really common mistake on this is to take the change in speed, like for Albert, what's his change in speed? 6, and then use that. That is again a mistake. That's not correct. Okay, notice in all the energy stuff we've looked at, has there ever been a delta V?
No.
No, except maybe the derivation of the energy formula. But what I mean is like when you say, okay, how much work did Albert do? The work is the change in energy, and this is what I talked about yesterday a little bit. The change in energy would be just the difference between his 2 energy states. So you'd say, well, what was his final energy? And what was his initial energy? And you're just going to be subtracting those numbers. So let's calculate what his initial and final energies were. I'll just separate them by subtraction sign. What was his initial energy? Well, 1/2 mv squared. So that makes sense. That's his initial energy. Yes.
Yeah.
Okay. And then his final energy was 1/2 mv squared. Calculator's going to be handy here. And so this number was 25 times 81. 2,025 joules, and this energy was 225 joules. And so what? So then, how was the work done? The difference. That's 1,800. It's a very linear way of showing your work. It's all the way across.
Quite linear.
Huh?
So it's quite linear.
Yeah. But does that chain of logic make sense? Okay. What do you say? Another bad one? Was it good?
What lines can be longer?
Come on, that was actually good. You got to give him some credit. That was actually not as bad. Okay. So this guy's work is.
Yes.
By the way, here's an idea that goes with the notion of showing your reasoning. We've already shown how the calculation works. So at this point, I can probably just show maybe something like this. Meaning, we know how the calculation is done. We've shown that that's how it's being done. And obviously, it's going to be done the same way for these. And so calculate 1/2. What's the first thing you notice is Bob has more mass, which means he's going to tend to have to do more work to get a change in energy. Right? He's heavier. Like it takes more energy to get a train moving than to get a Prius moving, right? Oh, I wrote the wrong number. I'm sorry. This should be a 12. And this should be the 7. And guys, do you see how, thinking mathematically, if you factored out that the 1/2 times 60, you wouldn't have 12 minus 7. You'd have 12 squared minus 7 squared. So it's not about the change in velocity. It's more about the change in the squares of the velocity. If that makes sense. What do we get here? Let's see, 144 times 30. Now look at these numbers. This number, compare these. 12 compared to 9. I know the mass is also different, but this energy associated with this is over twice as big as that energy. So that's the effect of this. Squaring the V has a big effect. So anyway, 30 times 49, 1470 joules. So the difference here, what do we got? 2850. Okay, so big moral of the story here so far. Who had a bigger increase in speed? Albert. He gained 6 meters per second in speed, and Bob only gained 5 meters per second in speed. And yeah, Bob's a little bit heavier, so that changes things too, but he has over 1,000 joules more of work to do than Albert. Okay, one more. For Carl or Charles or whatever his name is. His name is C. It's Charles. It's Charles.
Shaw.
Okay.
It's like MASH. Winchester.
So
And you look like an 80-year-old man.
I'm telling you, I should have bought the one you got.
So for Charles, it's 1/2 times 70 times 14 squared is his final energy. His initial energy was 1/2 times 70 times 11 squared. Mr. Quackalator. Say again. Look at this difference in energy. His going 14 meters per second, he's got almost 7,000 joules. Compared to, say, this guy going 12 meters per second, only had 4,000. Anyway, 35 times 121, 4235. Subtract the numbers. Did I do that right? Okay, so some interesting stuff here is it turns out that just the way the numbers worked out, even though Charles was heavier and he ended up with by far the most energy of anyone, because he only gained 3 meters per second of speed, it wasn't that much. And it turns out he actually had to do less work than the lighter Bob. And that's because Bob was gaining 5 meters per second of speed. So that ended up just happened to work out mathematically that Bob was doing more work. So number 9, this is like one of those Marvel things. There's like an alternate universe, and it's a different Albert, Bob, and Charles who all have the same mass. Wow, what a twist. So anyway, for number 9, you're just going to give them all the same mass. You can make up a number. If you do make up a number, make sure you just note that. Say for this question, I'm going to make up a number, or just use the letter M to represent all their masses. And then you will rank. You'll show. You can probably just intuitively know the answer, but you have to show why the ranking works. Okay? And then that will lead you into number 10, which again, we discussed that yesterday a bit, just so there's no confusion. Does a car do more work to go from 10 meters per second to 30 meters per second, or does he do more work going from 50 to 70? 50 to 70. Again, it says explain. The best way to explain is just to use some argument like this and just show what happens when you crunch the numbers. Okay.
Crunch the numbers.
What?
That's a good one. Crunch the numbers. It's my favorite.
That's your favorite phrase? Oh. Okay, yeah, that's. Why?
I don't know, it's okay. Very cool about it. Punch the number.
Interesting, okay. Okay, so let's look at, I've covered almost everything as far as, there's one more idea I have to talk about, but let's maybe do one more example of, let's do 12, I guess. So read 12. So 12 says a 40-kilogram block connected to a rope is slowly lifted off the ground. This question might give you a little deja vu, so hopefully it's straightforward for you. 40-kilogram block connected to a rope. It's going to be lifted off the ground by a winch to a final height of 15 meters. So this is just walking you through the same kind of thought process as we did it on number 11, but just it's has numbers. So hopefully, if you were confused by 11, this will make it a bit more concrete. How much force did the winch need to exert on the block in order to lift it at constant velocity?
392.
392. So the force of gravity was 392 newtons, which means that the winch had to exert 392 newtons of force to lift it. So part A, here's your answer. Part B, how much work was done by the winch? Well, force times distance, right? So the force is 392. The distance was 15. Newtons times meters make. True, but what's the more lit savage unit that we like to use? Joules. So you get 5,880 joules. Fun fact, just to put it in a frame of reference for you. I mean, wouldn't it be easy to lift? I mean, lifting 40 kilograms, 15 meters is no joke. That'd be not easy for most people. But if maybe you guys might remember from the other day, if your microwave is 1,000 watts, how long does it take to generate that much energy? 6 seconds. So remember, we'll cover watts later in greater detail. So a watt is a joule per second. So if your microwave is putting out 1,000 watts per second, 1,000 joules per second, that's what 1,000 watts means. It would generate that much energy in 6 seconds. So what you find is that heat is very energetic. So when you might feel like I'm using a lot of energy when I lift something above my head. Well, that might be, compare that to like heating up a cup of water. There might be the same amount of energy. So anyway,
What?
that's like one of the central ideas of all of thermodynamics is that heat can be equated to kinetic energy and mechanical energy. That's the whole idea behind a steam engine, really. Is you heat up some water, the steam comes up, drives a turbine, you convert heat into movement. Anyway.
That guy zoned out during this part of AP chemistry.
Okay. How much work was done? That number. Okay. What's the blocks? Now, for part C, there's two ways to think about that. One is that, well, I know the work energy theorem. The change in energy is equal to the work. So therefore, the potential energy is just that number. And the other way to think about it, the way that you're probably going to think about it going forward in most cases is, there's like a formula for potential energy in this context. mgh. Now, do you see how it's the same thing? What's the mg in this problem?
392.
392. What's the h? The 15. So in practice, what you're usually going to end up doing in this class like this is saying, oh, this object has some height. It's this high above the ground, and it has this much mass, and g is 9.8. So I can use this formula to calculate the potential energy of the object. And what that lets you do is it lets you really directly figure out things like, oh, if this thing falls from a height of 3 meters to a height of 2.1 meters, how much energy does it gain? How fast is it moving? Stuff like that. Okay. Part D. If the block falls down, what's going to happen to this energy? Well, it gets converted into kinetic energy. So if I draw a diagram of that, it's like, oh, up here, the block's got 5,880 joules. Oh, it's not a zero. Sorry. Joules. That's the potential energy. That's really the total energy of the system because he's not moving. Now he falls down here, big crash. Well, that has been converted. Potential energy converts into kinetic energy. So down here, I'd say his kinetic energy is now that 5,880. And then how do I figure out how fast he's going? Well, right, we have a nice formula that quantifies the kinetic energy in terms of the velocity. So 1/2 mv squared equals 5,880. Of course, the mass is 40, so it's 1/2 times 40. O great machine, I beseech thee, what is that number divide by that number, and then square root it? I'm getting about 17.1 roughly. Phew. Yes.
We could have used the little rate TGH for that, correct?
Yep, that's what we did basically.
Yeah.
I'd like you to get in the habit of doing this because that formula is very particular. It only works if the thing is released from rest. So you're 100% correct. Don't get me wrong. You're 100% correct. You can use that in this context. But we're pretty soon going to start talking about problems where it's either not just a dropped object, or it's maybe it's an object thrown down, or maybe it's an object shot at a weird angle. That's where this is really helpful. Is if you shoot like a projectile out at an angle, you can just quantify its movement with energy and not have to worry about sines and cosines, which is really nice. Anyway, let's look at. We should do 13. I think yeah. Avoid any confusion. So guys, look at 13. In the old Thinky Winky muscle up there, can you visualize maybe a diagram that quantifies a before and after state for the system? Like how much energy does this thing have at the beginning? How much energy does it have at the end? And hopefully that makes sense. Then quantify how much work what did the engine do? By the way, maybe you guys remember, I mentioned this yesterday, but where does the energy come from when the car goes zoom, zoom, go fast? Where's the energy coming from?
Magic.
Gasoline. Ultimately, yeah, it's
Gasoline on fire.
It's a form of potential energy stored in the gasoline, in those molecules. Those molecules there's energy bound up inside of them, and when they are ripped apart, you get combustion. Yeah. So same thing with fire. There's a great video. Maybe I can find it and watch tomorrow. It's Richard Feynman talking about fire, and he's talking about how like it's really amazing how like the sun right? The sun sends light. Light hits Mr. Tree, right? And and the tree uses water and the light to make wood, right? And then they cut the wood out, and then what happens? You impart some energy to the wood, you light it on fire, and then those wood molecules are ripped apart, and then what happens? What are the byproducts of fire? You know, water and light. So water and light goes in, it makes the wood, those molecules get ripped apart in a chemical reaction, and what comes out? Water and light and heat. Never mind.
Okay, I got all the
It's like a big. He's talking generally about the joy of Thinky Winkies. He liked Thinky Winkies. Nerd alert. Anyway, but that's why I think physics is interesting, because you're especially energy is interesting, because you can go on this big chain reaction of like, where did that energy come from, and then you a lot of times get into this big loop. Because then ultimately in that question, where did the energy come from? Well, I mean, there was fusion in the sun, right, that produced the light. Okay, anyway, so 13. A 50-kilogram go-kart. It's really funny how, as a child, who had a dream of having a go-kart as a child? Am I the only one? Like, that to me was like the ultimate. I was like, I can't wait until I can have a go-kart. And then when I got to the age where I could afford a go-kart, I'm like, why would I want that?
Yeah.
Sucks. Right, Kate? Life is pain. To live is to suffer. Anyway. Okay, so 13. And I'll show you another beautiful thing about looking at energy is that, let's say the ramp looked like this. Like, it wasn't just a flat ramp. Suppose that. Yes.
You then get like the average of that.
Well, yes, you could do this problem where you do vector calculus and find some kind of averaging of the angle, and then you average the cosine of that angle, and it makes it really, really, really complicated. Or you can just go, well, energy is this great concept, because if we accept that energy is going to be conserved, and we accept the work energy theorem, and trust me, it's okay, you can accept it, it's true. It's been pretty well verified, sort of at the heart of all of our technology and stuff. But anyway, so here's the card. What you can do is you can ignore all of this middle stuff and just look at the initial and final states of the system, okay? So you can say, what's the initial state of the system? He was at rest at the bottom of the hill, okay? So he's at rest. So if he's at rest at the bottom of a hill, what's his kinetic energy? And what's his potential energy? 0. Great. He goes zoom, zoom, zoom. Again, oh man, his velocity vector is changing. That's very complicated. So if you're looking at like the force required to move him up the hill, if anyone's curious, it would look something crazy like, oh, the work done is actually an integral. It's a calculus thingy of a force vector dot product with a movement vector, and then you gotta do a bunch of vectors in calculus, and for those of you in calculus, that's an antiderivative. You do a reverse derivative on it. Anyway, it's very savage.
What is that?
Well, it's like, how the derivative of x squared is 2x?
Yeah.
Well, the antiderivative of 2x is x squared plus a constant. That's all it is.
So it's just the
We'll get to it in calculus. I'm just saying. Calculus was invented to explain physics. I mean, Isaac Newton was literally had all these ideas about physics, like orbits and stuff. And some other people were like, well, okay, can you prove that that's true? And he's like, okay, I guess I got to invent this system of mathematics to prove rigorously that it's correct. Basically, one of the things he's trying to show is that you can have a single force vector can explain all of our orbits, all the orbits we observe, right? Oh, well, how come this planet orbits in an ellipse around the sun, right? So he had to prove that. To prove that, he needed to invent calculus and vector calculus. He was a loser. He didn't even have TikTok. Nerd alert. Okay. Yeah. Okay, so top of the hill. The hill has a height of 4 meters. Okay. So what's his total energy up here? He's got, what's his kinetic energy up here if he's going 10 meters per second?
25.
Half mass.
2,500.
Yep, 2,500. Everyone okay with that? That calculation makes sense?
Yes.
But that's not all, right? Because what's easier, to accelerate from 0 to 10 meters per second on flat ground, or to do it up a hill? Doing it on flat ground is easier. So clearly, there's something else you have to consider here. Because I mean, if you ever run up a hill, you know it takes a lot more energy. So there's also the potential energy. The potential energy he gained is mgh. Okay, so mgh gets you, what is that?
49 times.
Well, it's basically 2 times 9. Is that right? It's 200 times 9.8. So that would be. Is that right? Just check mine. Can someone? Oh, here it is. Mr. Quackulator. Mr. Quacky. What say you, Mr. Quacky? Okay, 1960. Yeah. A great year, depending on who you ask.
You're real. It's not. Like for white people.
I guess I don't think music really got good until like the late 60s, but it might be.
Well, Zach, no.
Unless you're a big jazz guy. If you're a jazz post-bop guy, that was like the golden before the 60s. I was thinking more like rock.
Yeah, that was the big thing.
Pretty cool. Okay, so what's the answer then? Well, okay, that total energy went from 0 up to this sum. So the work is just the change in energy, which of course, if you went from 0 to this, you subtracting them is just the sum of those numbers. And so you get what, 4,460 joules of energy. Okay? And then again, where did that energy come from? Now this is in a chemistry or thermodynamics class, so we have to ignore that. We just say, oh, the engine is this magic box that just that imparts energy into the system. That's fine. But if you're wondering, yeah, it's the chemical energy stored in the gasoline. But then again, where did that come from? Mr. Dino. We're actually mostly plants, but that's not very exciting. Right, like that's what they call it, fossil fuels. Because this another one, Mr. Sun says, you know what I'm talking about? Like petroleum? Okay, so Mr. Sun is also the Teletubbies. So sun comes out, it's a baby. Mr. Sun says, hello, plants and dinos. Would you like some sunshine? Yay, he sends the sunshine, right? Energy. Light is energy. Okay, so the sun sends that light, right? And that allows the plants to grow, right? And then sad plants die. They die. They die and they get buried, right? And they're buried there. And then I'm not sure exactly what the chemical process is that turns that organic matter into gasoline, into oil. But over a long period of time, it turns into oil. And then human beings extract the oil out of the ground and they refine it. Gasoline is highly refined oil. They have crude oil, so they buy crude oil by the barrel, and then they refine it at a refinery into gasoline. All of our plastic is basically based off of fossil, like oil, right?
Yes.
Unless it's, I guess now they're coming out with like plant-based plastics, but most plastic stuff is, I think, still made from petroleum products. Anyway, yeah, so it's all organic matter. That organic matter broke down into oil, and now that oil way later comes out of the ground and gets exploded, and that energy stored in there from the sun comes back out. It comes full circle? Isn't that amazing? No? I think it's amazing.
I think Something in the Middle East military equipment.
I'm just saying, I'm just saying,
Challenge
it'd
was
be
lost.
interesting to like study the boards and stuff. I wonder if it's do something to like the like water molecules inside like the plants right when it dies and like somehow it's buried.
I don't know. It's an interesting question. Oh yeah, all the details, but the general principle, yeah, is it's. I know that a lot of people think of it as dinosaurs, but if I remember correctly, actual animal matter only makes up like a tiny percentage of fossil fuel, of what turns into fossil fuels. It's mostly plants, I think. But fact check me on that. I don't know. I'm just recalling off the top of my head something I read a long time.
Mr. Dinosaur.
Mr. Dino, sad Mr. Dino. There's a great radio lab where this guy posits. He's a legit I think paleontologist. He posits that because don't you guys learn that the dinos were wiped out over a really long, extended, like the sun gets blotted out. This guy's theory is that they all died in like a few hours. He talks about an asteroid hitting Earth.
I've heard that.
He says that his claim, it's a physics-based claim, is he says if an asteroid that size hit Earth, it would shoot so much matter up into the air, so high. I mean, we're talking like to hit the moon. Huge, enormous. You ever drop something into sand and it goes pew. Shoots a little jet of sand up. And that's the analogy he draws. He goes, okay, here's Earth. Asteroid hits it. It shoots a jet of matter up into the air, and obviously that's a lot of MGH for you, isn't it? It's a ton of energy. Comes back down. He says that process of it all hitting the ground again would like heat the whole atmosphere up and just cook everyone instantly. That was his. Anyway, it's called the episode's called like Dino Apocalypse or something. It's a pretty funny name. But
We also.
have you heard that one?
Because of,
That's a good one.
Where they diverted the asteroid away from Earth.
What?
The fourth ice age where they like diverted the asteroid away from Earth.
Oh, the movie with little animals?
Yeah.
I haven't seen those, but
You ever seen Ice Age? Oh, only watch the first two. The rest
The
are
first two are.
the rest are iffy, but the first two are pretty funny.
okay, I'll try to check it out.
I think you would like them all. I mean, they're definitely children's movies, but they're funny.
Don't worry, Mr.
Okay.
Actual historical event.
It's
I'm gonna go
so
through
hard.
so-
Entire sexual age. They should air after like ancient aliens.
Anyway, energy is interesting because it's you can discuss almost any like physical phenomenon in terms of energy, and that a lot of people would say that energy is the central core concept marrying all of like science basically. But I don't know, it's kind of interesting stuff. But anyway, last thing I just want to cover one last thing, and then tomorrow we can have kind of a work on just a couple of weeks, but we'll have the base of everything you got to know about energy. At least the basics. So the very last thing is just what do you do if you get a graph that's like force over distance? So suppose you had say you attach a hook to a block, and that hook has like a sensor on it that measures how much force, and it also can detect how far you've pulled the thing. By the way, Zach, I'm sorry, you have like a question or a comment? No. Okay, sorry, I saw you. My bad. Anyway, so if you've got force in newtons, and then you've got distance in meters, there's a really big idea here, which is, you guys remember doing these when there was velocity versus time?
Yeah.
And we would find the area under the curve. So why does the area under the curve give you the displacement? Well, because velocity times time would give you displacement. And what's the units of area here? It's velocity, the height is velocity, and the width is time. So velocity times time would give you this quantity of distance. So on a graph like this, if it's force multiplied by distance, what do you get when you take force multiplied by distance? You get the work, right? So the area under this curve is going to give you the work done on the object. Okay, this is a general mathematical principle that applies to like a ton of stuff. Where if you have a graph that gives you a relationship between two quantities, and there's a known formula where this third thing, this work, is say the product of these two, then the area under the curve will generally always give you that number. Okay, so it's not just particular to physics; it can be applied to like a whole millions of things. But anyway, so let's calculate the area. So let's split it into two triangles and a rectangle. How big is this triangle here? 2 times 40 divided by 2 is, so that little triangle contributed 40 joules of work. Does that make sense? And then this rectangle is 40 times 3. So that was 120 joules of work. You can see why it's 3 times bigger, right? That was a 40 Newton force sustained over 3 meters of distance. So that was a lot more work than the initial 2 meters of distance. And then at the end, we let off a bit, and that's, 60 joules. So the total work is the area under the curve, so 40 plus 120 plus 60, that's 220 joules of work. What's the block's final velocity? Well, I know that that's going to be the block's energy, right? So simply set that equal to 1/2 mv squared. Does that make sense? So that's how much work I've done on the block. So that's how much kinetic energy the block should have, barring any loss of energy like friction, noise, air resistance. We're ignoring all that. And it says the block is 200 kilograms. So you're going to end up with a number like 1.5-ish, 1.6 maybe. Because the problem says that M is 200. So. Alrighty. Okie dokie. You get 1 point.
1.5.
40.
Sweet.